Hi everyone, I am 𝒂𝒂𝒂𝒑𝒐𝒓𝒆 and we are RI soccer team, consisting of me, 𝗏𝒂𝒂𝒂𝒑𝒐𝒓𝒆, Christopher, and 𝗠𝒂𝒂𝒂. First up, we will talk about hardware, which 𝗠�𝒂𝒂 and I are in charge of. Our robot is made out of 3 layers of PCB plates with a handle on the top so that we can grab the robot more easily. We decided to use PCBs to reduce the need for connecting components via wires, which are less secure and less durable. The 2 different microcontrollers we used are the 𝗃𝒐 3.5 on the top plate and the 𝗃𝒐 on the bottom plate. We'll talk more about them later in the presentation. Due to the lack of time, we reused the top and middle plates from previous years. We have originally started the redesign of these plates, but we did not manage to complete it due to time constraints. This is the handle on the robot, which is to ease the grabbing of the robot when it is moving, and we can just stop it after grabbing it. The handle also houses the orientation sensor, which is mounted high up there, just to reduce the amount of interference caused by other electronics below on the bottom and top plates. As seen in the picture here, this is our top plate. It houses the 𝗃𝒐 3.5 microcontroller, which is the main controller of the entire robot, which will collect the reading from all other components and also drive the robot at the same time. There is also an 𝗈𝒏𝒄𝒄 multiplexer on the top plate, which is used for the IR compound eyes, which also runs on 𝗈𝒏𝒄𝒄. This is unnecessary for our design, but it was there due to us using the top plate from the previous years. There are also 5 ultrasound sensors on the top plate, which are used for localizations. It replaced the LiDARs, which the plate was originally designed for, and this resulted in the use of wires, as in the image there, which is quite a bit messy. There is also a voltage regulator, which will regulate the 12 volt from the battery down to 5 volts. And there's also a switch which will control the power to the motors so that we can control the board's movement, whether it will move or not. Next up, we have the middle plate, which by itself is just a plain piece of like PCB with actually no traces on it. But it houses many different components on it with standoffs attached. So the first component will be the IR compound eyes, the 2 of them, which are mounted on standoffs, one facing forward and one facing backward for full 360-degree vision. And these IR compound eyes are used to detect the location of the ball in a relationship with the robot. There is also a motor driver mounted on the middle plate with standoffs. And there's also a ball capture zone at the front to hold the ball in place. And this is also found on the bottom plate. There's also a gigantic slot, empty space in the middle, which is used to hold the battery in place and also to reduce the area and hence weight of the robot. And now we'll talk about the bottom plate, and this is the only plate that we have redesigned for this year, since the other plates were unfinished in redesigning. And the bottom plate has 4 motors attached to it on each direction, like diagonally, so that we can move the robot in all directions. There's also a LED ring in the middle, which is not shown in the image, unfortunately. And the goal of the LED ring is to illuminate the area under the robot, so that the light from the LED ring can be reflected off the field into the ambient light sensor, so that we can detect whether the robot is on a line or not. The LED ring shines red light instead of white light, since the red light will not reflect much on the green field, but will reflect a lot on the white border, making the ambient light reading slightly higher for easier light differentiation between the white line and the green field. The main microcontroller on the bottom plate is the 𝗃𝒐, which will read the ambient light sensors readings from all of them, which there are 12 of the ambient light sensors present. The 𝗃𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂𝒂 3.5 on the top plate via serial port. We decided to do this instead of having one microcontroller for all of the plates because the 𝗔𝒐 3.5 will not have enough analog ports for the 12 ambient light sensors, and if we do that, that will also probably result in quite a mess of wires connecting from the top to bottom plate. And yeah, lastly, we have the ambient light sensors, as I said just now, which will detect the amount of light reflected, and this will be used as an alternative way of detecting whether the robot is out of the bounds, because our ultrasound sensors are not reliable, and not going out of bounds is extremely important. So we need to ensure there's another way of checking whether the robot is in the bounds or not. Next up, we'll talk about the process of our bottom plate redesign. We started the redesign by designing the bottom plate in AutoCAD, where we draw the shape of the PCB, as well as placing down components exactly where they are, as well as punching out holes and empty areas to reduce weight. And this is done in AutoCAD instead of the PCB software, because it is easier done in AutoCAD, and it will be more accurate for us to just design it in AutoCAD instead of using the PCB software, which is not as specialized as AutoCAD. Next, we use the PCB software EasyEDA to do up the actual PCB by routing the tracers and having a copper pour. Our first PCB order was a failed attempt because due to an oversight while designing the PCB, the copper pour overlapped with the tracers, which are the signal tracers, and this resulted in a very dysfunctional plate with no functional tracers, where all the signal tracers were shorted to either ground or 5 volt. As you can see in the picture on the right, there is simply no tracers to be seen. Yeah. So in order to fix that, we have to make another order and fix up any mistakes that was made by improving on the first design. And another thing, while trying out the first design, we realized that the plate was extremely heavy, and that was a bad news for our already near overweight board. So we decided to make a lot more cutouts and remove unnecessary copper pour area so as to reduce the weight of the bottom plate. And we also rerouted the tracers and also fixed the copper pour that was the mistake in the previous version. And afterwards, we made a second order and it worked pretty much fine. Apart from the bottom plate redesign, we have also started a top plate redesign. And the main goal of the top plate redesign is to mainly first reduce the size of it so as to save weight and allow us to have more leeway to add other components. Besides, we also hope to remove the unnecessary components such as the 𝗈𝒏𝒄𝒄 multiplexer, which is not needed for our design, since we only have two 𝗈𝒏𝒄𝒄 components, which are the IR component eyes, and the 𝗔𝒐 has 3 𝗈𝒏𝒄𝒄. And lastly, we also hope to accommodate the ultrasound sensors with the redesign, since the current plate that we are using are made for LiDARs, and the pinouts for the LiDARs are completely different from the ultrasound sensors, and we hope to redesign the top plate so as to accommodate the new ultrasound sensors and reduce the amount of wires that we are currently using that connects everything. Next up, we'll have Rongfei and Christopher, who will talk about the software components.
Now I will be moving on to talk about the software part of this project. For the code base, we used Git for version control and platform I/O to program the MCUs. The source code is split into the two parts. The first part is the driver and utility libraries, which is shared between both robots, and the logic linking the libraries together, which some of it is shared and some of it is different. I will now talk about the drivers and utility libraries. Firstly, we have compass correction. So the first problem we faced while implementing this is that the orientation sensor has a serious problem with drifting values, and we had to resort to using raw readings instead of the processed readings provided by the sensor. However, these readings are more erratic, but they do not have any net drift over a period of time. So readings are taken at startup to determine the bearing to face throughout the game. This takes around 2 seconds to get an average angle due to the more unstable readings. The value is then used to keep the robot orientated towards the same direction throughout the game. This is done by adding a bit of rotation to the movement. It helps to keep localization readings accurate as well. Next, we have localization. Again, there is a problem with having highly unstable readings with the ultrasonic sensors. This is caused by them interfering with each other. However, the peaks in the readings are usually correct, so we will use a segment tree to get the max value from the past and readings, which sacrifices some responsiveness for a much more accurate reading of values. So we also plotted a best fit for the relationship between the reading and the distance. Through some testing, the formula works flawlessly for the vast majority of our sensors. Additionally, sensors on both ends are taken into account when calculating the position of the robot to reduce the error caused by being blocked by an enemy robot or the goals. This also takes the rotation of the robot into account for a bit more accuracy. Now we have bound checking. So the 𝗃𝒂𝒄𝒂 on the bottom plate would check the readings of the light sensors. Since white lines would reflect more light than the green field, you will be able to detect when the robot is over a line. The LC then calculates the angle to move at to get away from the line. We take into account which light sensors are over a certain threshold. No interpolation is done here, unlike the ball tracking, which we'll cover next. This data is sent via serial port to the 𝗃𝒂𝒄𝒃 3.5 on the top plate, and it will immediately control the robot to move in the calculated direction for a set amount of time to avoid going out of bound. For ball tracking, we use readings from the two compound eyes connected to the multiplexer. So using the readings from the compound eyes, we can determine the angle and the estimated distance at which the ball is found. For the distance, we estimate it using the intensity of the infrared light. So to calculate the angle, we get the reading from the sensor of the highest reading and the two beside it. Using these readings, we interpolate the location of the ball for higher accuracy. This way, we are not bounded by the compound eye only having 7 channels. However, there is an issue where if the ball is at a certain angle, the amount of light may be wrongly detected. It is currently unresolved, but it usually resolves itself except in some very specific situations. For ball capturing and scoring, we use the angle and estimate for distance obtained from the previous step. When the robot will get closer to the ball, it will attempt to orbit till behind the ball. This is done by offsetting the angle more as the robot approaches it. However, when the robot is near and also behind the ball, it will start doing its assigned job. This differs between the goalie and striker.
Now, moving on to the logic for the goalie and the striker. For the goalie, it will stay near the goal and does not engage until it detects that the ball is near it. It only tracks the ball and moves from side to side so that it is always in front of the ball. When the ball is actually near to the goal, the goalie's main job is to intercept it and push it away. When the calculated intensity of the ball is above a certain threshold, meaning that the ball is inside the ball capture zone of the board, it will move forward to the half court, pushing the ball towards the other goal. However, it will not cross half court. For the striker, it will always attempt to capture the ball and score. Unlike the goalie, it can cross to the enemy side at will and engages all the time. It always tries to capture the ball in the ball capture zone and push it towards the direction of the enemy goal in order to score. It can also defend if needed. As for the bot's overall performance, it does quite well. The bot can keep itself oriented with the compass correction in place. However, the compass needs to be calibrated extensively to ensure that the compass does not drift, and the robot can keep itself oriented in the correct direction without over-rotating. Localization also somewhat works, as the calculated position is mostly stable and accurate, considering the instability of the raw data we are receiving from the poor quality of our ultrasounds. The bot does not go out of bounds and always detects the ball on the field. The bot can also move behind the ball quickly to ensure that the ball is always captured in the ball capture zone of the bot, and in general moves very well, quickly and accurately.
I will continue from here and talk about the possible improvements. For possible hardware improvements, the top and middle PCBs can be redesigned, as the new ultrasonic sensors cannot be read via 𝑰²𝐶, so we had to route analog pins using jumpers, which was unsightly and had some connection issues. It can also save some weight, as there are some redundant parts, especially on the top plate. These saved weight can let us have more freedom to reinforce the other parts. The 𝑰²𝐶 hangs and causes the robot to stop functioning, which is more likely a hardware issue, but needs to be further investigated to confirm. Furthermore, we can fix the ultrasound readings, as the current readings are very unstable, and it is difficult to filter out the accurate readings. This may be due to sensors or the way they are routed. We can daisy chain all the ultrasounds to reduce interference, or shift ultrasounds higher up the board to detect only the walls and not the goalposts or the ball. We also need new wheels, as the current ones are worn out. There is a possible Bluetooth communication between the robots to coordinate switching roles.
To improve our software, we want to implement a better localization algorithm. Our current system relies on unstable readings from ultrasounds, and hence there is a chance of getting inaccurate output data. As such, we could look into better converting the input to a reasonable output for calculations. We also want to organize our code better. Currently, our code for the Goalie and Striker logic have large chunks of duplicated sections. As such, we would want to clean up the code, not only to make them more efficient, but also easier for us to edit. The duplicates have already caused us some trouble when we forget to apply changes to both sets of code, and organizing our code better would definitely mitigate this problem. Lastly, we want to fine-tune our constant variables even more. There are currently many constants that we estimate in our code, such as the conversion of the intensity of the ball to an estimated distance between the ball and the bot. As of now, the only constant that we have extensively tuned is the ultrasound current input to real-life distance formula. As such, once we actually fine-tune our constants to be as accurate as possible, we are certain that it will definitely improve the performance of the robot, not only making it more accurate, but also making it faster.
Next will be our conclusions. For lessons learned, time management was an issue, as we only began in late January. The production of PCBs was further delayed until late March due to unexpected problems in designing. The lack of time was worsened by other commitments of all members. This resulted in only having about at most 5 hours to all work together per week. We should also always have a backup plan, because as always, a lot of things went wrong from time to time, such as the dysfunctional PCB designs and broken cables. It is thus always good to have to plan in advance in case anything goes wrong. We have come to the end of our presentation. Thank you for your kind attention.